Making sense of scientific notation in algebra. For the sake of this demonstration, let's use very small exponents. No scientist would ever write 200 as 2 times 10 to the second power, but it'll make this demonstration easier. What we've learned is that when the problem involves all multiplication, we can move each of the components around to make our math easier. 8 times 2 is 16, and then what we have left is 10 to the third power times 10 to the second power. Now, in pre-algebra, we learned that we could expand this out.
And then it would look like this. 10 times 10, that's 10 to the third power, and then 10 times 10, that's 10 to the second power.
And when we write them all together, it becomes 10 to the fifth power. Well, in algebra, we've learned an even niftier shortcut. When you have the same base and you're multiplying, all you have to do is add the exponents. We get that 5 by saying 3 plus 2 is 5. We're not done because your answer has to be in scientific notation. Your number has to be between 1 and 10. So this number 16 has to become 1.6. So if we were to expand this 16 times 10 to the fifth power out
into standard notation, it would be 1,600,000.
Decimal was here, and we are moving it 5 swoops.
1, 2, 3, 4, 5.
If we write it as an equation, it'll help us to see why the exponent moves the way it does.
So 16 times 10 to the fifth is equal to 1,600,000.
If we make this first number between 1 and 10, like scientific notation has to be, we have to make it 1.6. To get 16 to become 1.6, we essentially have to divide by 10. If you think about it, this entire side of the equal sign has to stay balanced with this side of the equal sign. So if we divide this first number by 10, we have to multiply our exponent by 10. So if you multiply 10 to the fifth by 10, it becomes 10 to the sixth. To verify that the numbers are the same, we can take 1.6 and expand it out. Now remember, that's 10 to the sixth power means 6 swoops, so that's
1, 2, 3, 4, 5, 6.
And we indeed get 1,600,000. Let's look at a few more cases. What if your answer was 0.34 times, say, 10 to the sixth power? Well, you know the first number has to be between 1 and 10. So in order to do that, we've got to multiply this by 10 because 0.34 times 10 actually gives us 3.4. And if we're multiplying this first number by 10, what we have to do is divide the second number by 10. When we are dividing exponents that have the same base, all you do is subtract the exponents. 6 minus 1 is 5. So your answer would be
3.4 times 10 to the fifth power.
Another example is
290 times 10 to the negative seventh power.
So you know that this is a very, very small number, but if we want it in scientific notation, this first number still has to be between 1 and 10. So in this example, we actually have to divide by 100 to get 2.9. Then in order to keep this entire expression balanced, we have to multiply this by 100. 100, as you all know, is just 10 times 10, which is 10 to the second power. So in this example, you have to multiply 10 to the negative seventh by 10 to the second. As you recall, when multiplying exponents with like bases, you simply add the exponent.
Negative 7 plus 2 gives you negative 5. So our answer would be
2.9 times 10 to the negative fifth. For our last example, let's do something crazy like
0.08 times 10 to the negative fourth power.
To get this first number in scientific notation, If we multiply 0.08 by 100, we get 8. We must divide this number by 100. So if we take 10 to the negative fourth and divide it by 100, which is 10 to the second power, remember, we must subtract the exponents.
Negative 4 minus 2 equals negative 6.
So the answer becomes 8 times 10 to the negative 6th power. I hope this helps you understand scientific notation a little better. With a little bit of practice, it'll become second nature. Thank you.